Hello everyone and welcome to the fourth tutorial of our basic electronics module. So today our session is based on capacitors and inductors. So today you will learn the basics of capacitor and inductors. Let's start our tutorial first. This is the table of content. These are the four categories which we are going to cover in this session. The first is capacitors. So what is capacitor? It's SI unit symbol, series and parallel connection. Then we will see different types of capacitors and applications of capacitors. In the third part, we will see the inductors. Like what is inductor? It's SI unit, its symbol, series and parallel connection. And then in the fourth and last part, we will see the different types of inductors and its applications. Let's start first with capacitors. So the flow of this session would be the definition, then SI unit and symbol, working of capacitor, series connection, then parallel connection. So a capacitor is a two-terminal electrical device, also a passive device, as we previously discussed, that can store energy in terms of electric charge. So it does what? It does stores electric energy in the form of electric charge. It consists of two electrical conductors that are separated by a distance. So it has two conductors, electrical conductors, and they are separated by some distance. The space between the conductors may be filled by vacuum or with an insulating material known as dielectric. So this kind of two electrical conductors are separated by medium or sometimes by a vacuum. If they are filled by insulating material, then they are known as dielectric medium. The ability of a capacitor to store charges is known as capacitance. So capacitance is the ability of any capacitor to store electric charge. Its SI unit and symbol. So the SI unit of capacitor is farad and denoted by capital F. The basic unit of capacitance is farad, but farad is a large unit, hence its practical tasks are also measured in millifarad, which is equals to 10 raised to minus 3 farad, microfarad, which is equals to 10 to minus 6 farad, also 1 nanofarad, which is 10 to minus 9 farad, and 1 picofarad, which denotes 10 is to minus 12 farad. So SI unit is farad and denoted by capital F. Now the capacitance and its formula. Capacitance is the ratio of the charge in electric change in the electric charge of a system to corresponding change in its electrical potential. So the capacitance C is the change in charge divided by change in the electrical potential. So C in farad is equals to Q, which is charge always in coulombs, and divides by voltage in volts. The conducting plates means two electrical conductors. The two conducting plates have some charges, which is Q1 and Q2, usually one for one plate and Q2 is for the another plate. The electric field in the region between the plates depends on the charge given to the conducting plates. We also know that potential difference, which is V, potential difference V is directly proportional to the electric field. Hence, we can say that this constant of proportionality is known as the capacitance of the capacitor. So, the voltage or V is always proportional to the electric field, and here electric field is charge, electric charge. So, hence V is proportional to Q, where proportionality constant is farad, which is C capacitor. Now also you can use this pyramid to remember this formula between capacitance, voltage and coulomb. So C is equals to, you can also see the Q charge is equals to C divided by V using this formula. See, Q is equals to C into V. Q is equals to C into V. Also V is equals to Q divided by C, or C capacitance, or C is equals to Q by V. So this is how it represents the pyramid of Q, C and V. Now the equation for parallel plate capacitor. The formula for the capacitance of a parallel plate is equals to C is equals to A epsilon 0 divided by D, where A is equals to area of parallel plate, epsilon 0 is permittivity, and D is equals to distance between both the parallel plates. Here both the parallel plates means the electrical conductors, which are separated by a distance, and the distance is filled with sometimes vacuum or sometimes by any medium. So the capacitance of a parallel plate is equals to A epsilon 0 divided by D. Let's see the two different connections of capacitors. First one is series and the next one is parallel. So what happens when number of capacitors are connected in series and what happens when number of capacitors are connected in parallel. Let us first see the capacitors connected in series manner. Here is a representation of n number of capacitors connected in series. In series, the capacitors or any element shares only one common node, hence the connection is known as series. Here these capacitors are connected with sharing one common node. So between C1 and C2 there is this one common node, between C2 and C3 there will be one common node, between these two there is one common node, and between Cn minus 1 and Cn there is one common node, hence this is a series connection. When capacitors are connected in series, the total capacitance decreases. Why? Because the formula of C total or effective capacitance of n number of capacitors connected in series is equal to the inverse of sum of individual inverse sum, and hence the total or effective capacitance decreases. Whereas capacitors in parallel. So in parallel, capacitors shares more than one common node. Here this is the common node and also this is the common node between C1 and C2, hence they are connected in parallel. So C1 C2 up to Cn minus 1 and Cn, they are connected in parallel connection. Whenever the n number of capacitors are connected in parallel, the total or effective capacitance would be equal to or is equals to this individual sum of capacitors, means C1 plus C2 plus up to Cn minus 1 plus Cn. So this is the total or effective capacitance in a circuit. When capacitors are connected in parallel, the capacitance increases, or the total capacitance or circuit's effective capacitance increases, because it is the sum of individual capacitance. Total capacitance is the algebraic sum of n capacitors, hence the total or effective capacitance increased. The second category is types and applications of capacitors. So let us see different types of capacitors and where the capacitors are used. So there are two main types of capacitors, which are first is depending upon the value, whether it is fixed type capacitor or whether it is variable capacitor. And the another one is depending upon the material, means which kind of material is used to build or to manufacture the capacitor. So in this type there are there are several different categories, which are tantalum, aluminum, ceramic, trimmer, thin film. These are the type of capacitors depending upon the material. Also the other types are electrolytic and paper capacitors. Applications of capacitors. So the capacitors are used in variety of applications, for example as an energy storage, as a sensor, for power conditioning, or to process a signal. So they are used to store electrical energy. Individual capacitors do not hold much energy, providing only enough power for electronic device during temporary power outage or when they need additional power. Many applications use capacitors as energy storage, and a few of them are as follows. For example, audio equipment, camera flashes, power supplies, magnetic coils, and lasers. One of the important applications of capacitor is the conditioning of power supplies. Capacitors allow only AC signal to pass when they are charged and blocking DC. So when the capacitors are charged, they only allow AC signals and blocks DC signals, and hence they are used to condition the power supplies. This capacitor effect is used in separating or decoupling the different parts of electrical circuits to reduce noise as a result of improving efficiency. Capacitors are also used in utility substations to counteract inductive loading introduced by transmission line. Also, capacitors are used as sensors to measure a variety of things, including humidity, mechanical strain, and fuel levels. Two aspects of capacitor construction are used in the sensing application. The first one is the distance between the parallel plates, and the another one is the material between them. The former detects the mechanical changes such as acceleration and pressure, and the latter is used in sensing air humidity. Means if the two means the construction is based on the distance between the parallel plates, then it detects the mechanical changes such as acceleration or pressure. And if it is built in a way that the material is in the main focus, then it is used in a sensing air humidity. Also, there are advanced application of capacitors in information technology. Capacitors are used by dynamic random access memory DRAM devices to represent binary information as bytes. Capacitors are also used in conjunction with inductors to tune circuits to particular frequencies, an effect exploited by radio receivers, speakers, and analog equalizers. So, this were some of the applications of capacitors where capacitors are mainly used. Now, our third part is inductor. In this section, we will see the inductor's basics, definition, SI unit symbol, and series and parallel connection. So, this is the flow of our session. An inductor is a passive component that is used to store energy in the form of magnetic energy when electricity is applied to it. So, whenever electricity is applied into it, it is used to store magnetic energy. One of the key priorities of an inductor is that it impedance or opposes any charge, any change in the amount of current flowing through it. So, it is a key priority of any inductor, which is it opposes any change in the amount of current flowing through it. Means it does not allow current to change. Whenever the current across the inductor changes, it either requires charge or loses the charge in order to equalize the current passing through it. The inductor also called a choke reactor or just a coil. So this is how the inductor is represented in a schematic way, whereas the two vertical line is used for capacitor, while this kind of coil section is used for representation of schematic inductor. So this is air core inductor. When there are two vertical stripes after this coil, then it denotes as iron core inductor. If there are stripes just like this, then they are ferrite core inductors. And if coil has an arrow, then it is variable called inductor. So SI units and symbol. The SI unit of inductor is Henry and denoted by capital H. The SI unit of inductance is Henry, but Henry is large unit. Hence, the sub units are also used, such as millihenry, microhenry, nanohenry, and picohenry. Now, what happens when inductors are connected in series and what happens when inductors are connected in parallel? So, first we will see the n number of inductors connected in a series. Here in the image, you can see that from L1 to Ln, the inductors are connected in series because they are sharing only one common node. So, L1's ending point is connected to the L2's connecting terminal first. Similarly, the Ln-1's ending terminal is connected to the Ln's first terminal. hence it is series connection. So whenever the n number of inductors are connected in series, the total or effective inductance in the component or in the circuit is equals to the algebraic sum of individual inductors L1 plus L2 plus up to Ln. So when inductors are connected in series, total inductance increases, similar to resistors. If you remember in resistors, when you connect n number of resistors in series, the total or effective resistance of a circuit increases. Same here, inductors connected in series and number of inductors connected in series increases the total or effective inductance. Total inductance is algebraic sum of individual inductance in each inductor. Now inductors in parallel. Parallel connection means the circuit component or element shares more than one common node. As you can see here, it is sharing this common node and also they have this common node. Hence, this representation illustrates parallel connection. Now L1, L2 up to L and they are connected in parallel. So whenever the n number of inductors are connected in parallel, the total or effective circuit inductance decreases, similar to resistors. And the total inductance is the inverse of the sum of individual inverse of inductance, where L is inductance in Henry. So inductance in parallel decreases, whereas n number of inductors connected in series, the total inductance increases. So these are the formulas for R resistors, L inductors and C for series whenever they are connected in series, parallel and its particular formula. So resistor is denoted by R, capacitor is denoted by C, whereas inductor is denoted by L. This is how they are symbolized in a schematic way. This is resistor, this is capacitor and this is inductor. And these are their particular formulas. Now let us see the fourth and last part of this session, which is types and applications of inductors. So there are four types of inductors, which are iron core, air core, iron powder and ferrite core. See, these are the types of inductors based on the material used for the core construction. So the first one is iron core inductors. So as the name suggests, the core of this type of inductor is made of iron. These inductors are low space inductors that have high power and high inductance value, means its inductance value are very high. However, they are limited in high frequency capacity. These inductors are also used in audio equipments. Now in air core inductors, there are air as a core medium. So these inductors are used when the amount of inductance required is low. So their value of inductance is comparatively low. Since there is no core, it does not have a core loss. Means air means there is nothing as a core element. Hence, there is no core loss. But the number of turns the inductor must have is more of this type when compared to the inductor with the core. This result in high quality factor. Usually ceramic inductors are often referred to as an air core inductor. So mostly the ceramic inductors are known as core inductors. Now the another type is ferrite core inductors. In this type of inductor, ferrite materials are used as a core. So this is the core of the inductor and the core is built out of the ferrite material. The general composition of ferrite is XFe2O4, where X represents transition material. Ferrites can be classified into two types, which is soft ferrite and the another one is hard ferrite. Now the fourth type is iron powder inductors. So in this type of inductor, the iron powder is used to form a core. So in this type of inductor, the core is iron oxide. They are formed by very fine and insulating particles of pure iron powder. High magnetic flux can be stored in it due to the air gap. The permeability of the core of this type of inductor is very less. They are usually below 100. They are mainly used in switching power supplies. So these were the different types of inductors. Now let us see choke. A choke is a type of inductor that is used mainly for blocking high frequency alternating current. Means choke are used to block AC current. And which kind of high frequency? So choke is used mainly for blocking high frequency AC. In an electric circuit, on the other hand, it will allow DC or low frequency signals to pass. So what will choke do? A choke will block high frequency AC current and it will allow DC or low frequency signal. As the function of this inductor is to restrict the changes in the current, it is called as choke. Means it is mainly to block changes. Hence they are named as choke. This inductor consists of a coil of insulated wire wound on a magnetic core. The main difference between chokes and other inductors is that in their cases they do not require high Q factor construction techniques meant to reduce the resistance in the inductors found in the tuned circuit. So this was all about the types of inductors. Now let us see the applications, means application area of inductors. So the first application is to control the signals. Coils in an inductor can be used to store energy. The function of the inductor depends upon the frequency of the current passing through it. That is, for higher frequency signal will be passed less easily and vice versa. Means whenever you want to control the signal, you can use inductors. To store energy, inductor stores energy in the form of magnetic energy. Coils can store electrical energy in the form of magnetic energy using the property that an electric current flowing through a coil produces a magnetic field, which in turn produces electric current. In other words, coils offer a means of storing energy on the basis of inductivity. So this was all about the basics of capacitors and inductors. Thank you so much. We will see you in the next tutorial.